Hey everyone, welcome! You ever play a game or watch a movie and just get lost watching the smoke swirl? Or maybe it's the fire from an explosion that looks so real, so complex, you can't help but wonder how they did it. Well, today, we're gonna peek behind the curtain and you'll be surprised to find out that the science behind all that magic is actually brilliant and way simpler than you think. All right, let's get into it.
Just look at this. I mean, wow. This isn't some photo from the Hubble telescope. It's a computer simulation. So that's the big question, right? How can a machine that only thinks in ones and zeros create something that feels so alive, so fluid? And how can it possibly do it fast enough to keep up with you in a video game? That's the puzzle we're going to solve today.
To really get how this magic trick works, we've got to go back to 1999, to a totally game-changing paper by a researcher named Jos Stam. It was called Real-Time Fluid Dynamics for Games, and believe me, it completely changed everything for visual effects.
You see, in the real world, any fluid, and I mean anything from water flowing in a river to smoke rising from a fire, it's all dictated by this incredibly complicated set of physical laws. We've known about them for ages, but actually solving them, that's a whole different beast.
And there they are, the infamous Navier-Stokes equations. Okay, don't panic. You do not need to understand any of this math, I promise. The only thing you need to know is that these things are insanely hard to solve. If you tried to calculate them perfectly for a game, you'd melt even the beefiest gaming PC.
And this, right here, is where Jos Stam's genius comes into play. He had this incredible insight. He realized that for stuff like games and movies, the goal isn't to be perfectly accurate with the physics. Nope, the goal is something else entirely.
And this slide just nails the trade-off. On one hand, you could go for strict, perfect physical accuracy, but that's going to be slow, super complex, and worse, it's often unstable. That means your simulation could literally just blow up into a mess of pixels. Or you could aim for something that's just visually convincing, something that's fast, totally stable, and, looks awesome to our eyes. Which one do you think a game developer is going to choose?
And Stam puts it perfectly in his paper. He says what really matters is that the simulation looks convincing and runs fast. That's it. This little shift in thinking from physically perfect to looks good enough is the key that unlocked this whole world.
So, how do you do it? Well, the paper is brilliant because it takes this huge, scary problem and breaks it down. He said, okay, forget about making the wind itself move for a minute. Let's just solve a simpler problem first. How do we move something like a puff of smoke through a wind that's already there?
And it all comes down to these three elegant steps that just repeat over and over again. First, you add a source. That's just adding new smoke to the world. Second, you diffuse it, which just means you let it spread out a little bit, kind of like a drop of ink in water. And then the most important step, you advect it. That's just a fancy word for moving it along with the wind.
Yeah, let's zoom in on that last word, advection. It sounds super technical, but I guarantee you already get it. It's just the idea of something being carried by a current. Seriously, just picture stirring cream into your coffee. The swirling coffee is the velocity field, and it's carrying the cream along for the ride. That's advection. Simple, right?
Okay, so let's see this in action. What we're looking at is a grid. The white splotch is our smoke, and all those little red arrows, that's our wind, our velocity field, and it's flowing in this cool S shape. So the question is, in the next split second, where is that smoke going to go?
Now this is the really clever part. The way the computer figures this out is kind of backwards. Instead of trying to push the smoke forward, which can get really messy, it does the opposite. For every single spot on the grid, it asks, okay, where would the smoke that's here now have come from a moment ago? It traces a path backward through the wind to find out.
And boom, here's the result. By doing that simple look backwards trick for every point, that patch of smoke gets stretched and swirled along that S-shaped path. It looks totally natural, it's super fast to calculate, and here's the best part. It's always stable. It will never ever blow up.
So that's pretty cool. We know how to move smoke through a wind field, but that brings us to the real million-dollar question. How do we get the wind itself, the fluid, to move and swirl and look real? Well, this is where the paper goes from clever to pure genius.
So here it is, the big idea. What if we could take those exact same simple steps we just learned, add a source, diffuse, and advect, and just apply them to the wind itself? And that's the secret. You just treat the wind's own motion, its velocity, like it's another density, just like the smoke. So what moves the wind? The wind moves itself. It's called self-advection. The flow literally picks itself up and carries itself along. That simple rule is what creates all those beautiful, complex, swirling patterns we see.
Okay, we are so close. Self-advection gets us like 90% of the way there. But if we stop right here, the fluid can still look a little wrong, a bit messy. It's missing one final, crucial ingredient to sell the effect.
And that secret sauce is a step Stam called projection. Basically, the idea is that real liquids and gases don't just appear out of thin air or vanish into nothing. So this step is like a mathematical cleanup crew that runs at the end of every frame. It gets rid of all the weird, messy bits of the flow, and in the process, it naturally creates those gorgeous, rotating, swirly vortices that just scream real fluid. When you combine all these simple, stable steps, the result was, well, it was huge. This technique didn't just work on paper, it worked in real time, on the computers people actually had back then. And that was an absolute breakthrough.
And get this is the craziest part. The entire engine that drives these incredibly complex visuals, the whole thing can be written in just a little over 100 lines of code. It's a perfect example of how an elegant, simple idea can solve a massively complex problem.
And what this meant for games was that for the first time ever, you could have truly interactive fluids. You could run through a cloud of smoke and see it react and swirl around you. This wasn't some pre-recorded animation you were watching. You were actually part of the simulation.
And these ideas were so powerful that they became the foundation for the tools the pros use. The Maya Fluid Effects System, which is used to create unbelievable visuals in movies and TV shows, was built right on top of these core principles of being fast, stable, and looking great.
And here's the really wild part. Even though the goal was never to be perfectly accurate, the simulation is so good that it actually reproduces classic phenomena from physics textbooks all by itself. This right here is a von Karman vortex street. It's that alternating pattern of swirls you get when fluid flows past something. Stamp's simple code creates it perfectly, without even trying.
Which really just leaves us with one last thought to chew on. This entire revolution in computer graphics happened because someone was willing to let go of the idea of perfection and instead just focus on what was needed for the experience. It really makes you wonder, right? What other huge complex problems are out there just waiting for a solution that isn't about being perfectly accurate, but is simply good enough to be beautiful?